Hello, I am Leslie Hyde, and today I'll be talking to you guys about Markov chains. That is the statistical method that is used in this week's journal club paper. So yeah, Markov chains and the math behind them. Dun dun dun. So let's start with a basic definition. The first part is that the probability of an event depends only on the event immediately preceding it. We look no further back than that. The second half is that there is a fixed set of future states. Putting these two together, it means we know what something is and what it could be. We don't care what it was before the is, we only care what it is and what it could be. This is a three-state Markov chain. There are three states, A, B, and C. Now A can do three things. A can remain A can become B, or A can become C. B has also three choices. B can remain B can become A, B can become C. Each of these possibilities has a probability associated with it. So this is the probability of A remaining A, the probability of A becoming B, blah, blah, blah. This is called a transition matrix, the matrix of probabilities of states. Now, we know exactly what things are and what they could be, and so we know the totality of the system. So we know that the probability of A remaining A, or becoming B, or becoming C equals 1. We know the totality. Now let's apply this to DNA methylation. This is a Markov chain with respect to DNA methylation. We've got three states: unmethylated, hemimethylated, and fully methylated DNA. Now, unmethylated DNA has three choices. It can remain unmethylated, it can become hemimethylated, or it can become fully methylated through de novo methylation, which is spontaneous methylation. Hemimethylated DNA has three choices as well. It can remain hemimethylated, or it can become fully methylated in two ways. So it can do one thing in two ways through de novo methylation or maintenance methylation. This is exactly what DNTM1 does. It turns hemimethylated DNA into fully methylated DNA. That's what DNTM1 does. And the third possibility for hemimethylated DNA is for it to become unmethylated. It does this through demethylators. There are three types: TETs, epigenetic drift, and epimutations. Now in this paper, in the science that they did, they took out TETs. They eliminated them from the system. But I kept them in here because if you don't take them out, they are a factor that demethylates your DNA in a system. Then there's epigenetic drift and epimutations. Epimutations are actually caused by DNTM1, very infrequently, but it does happen. Most of the time, DNTM1 is doing maintenance methylation. Anyway, those are the three choices for hemimethylated DNA. And there's fully methylated, remain fully, go down to hemi or go down to un through these demethylators. Now, let's look at the transition matrix for our Markov chain methylation. We've got the probability of unmethylated remaining unmethylated, the probability of unmethylated becoming hemimethylated. You can see it all here. Let's fill in the probabilities. We've got the probability of unmethylated remaining unmethylated. We don't know that probability, but we do know the probability of unmethylated DNA becoming hemimethylated. That's B, so we get to fill that in there. The probability of hemimethylated DNA becoming unmethylated, going back down, that's TEE, that's the demethylators. The only weird one is here, the probability of hemimethylated DNA becoming fully methylated. That's one thing that can happen in two ways. That's the D plus the M, the D plus the M. Let's analyze this transition matrix with respect to math. We know that as the epigenome progresses, things become more and more methylated. So this matrix is upper triangular dominant. You can see it here. These D's and M's need to be larger than the demethylator factors in the system. Now, the scientists for this paper, they attacked this computationally, and what they did is first, they varied the de novo methylation, but kept the maintenance methylation constant. And what they discovered is that you must have de novo methylation in your system. It is essential to maintaining the DNA methylome. If you don't have any D, if there's no D here, then the demethylators take over and they completely demethylate your DNA. But as long as you have a little bit of D, you can get to a steady state of methylation in your system. The second type of computation that they did is they kept D constant and they varied the maintenance methylation factor. And what they discovered is that the maintenance methylation, DNTM1, needs to be doing its job in order to get a high level of methylation in the system. Now, these curves are steady states. That means that no matter where you start in the system, you can start with fully methylated DNA. But if your maintenance methylation, if your DNTM1 is not doing a good enough job, the methylation in your system will decrease down to this level. It'll reach a steady state of this amount of methylation, this partial state. You could start under that, and if it's the same amount of DNM, it'll come to this steady state. No matter where you start, if it's with these factors, you'll end up here. You start above, below, yes. So how did they do this math? It's actually pretty simple. So here is the transition matrix for our Markov chain methylation, and we're trying to reach a steady state. We want to know the percent of the final DNA that is unmethylated, hemimethylated, and fully methylated. So the way we do the math is we have matrices. So we're going to solve the system AX equals B. Really sweet. Now, the A happens to be the P, the transition matrix, and X, the vector we know, is the state of the system now. And what we're trying to solve for is the state of the system in the very next state, exactly what it's going to do next, what it will become. Now, because we're trying to reach steady state, we know that the state it is now must equal the state it's going to be in the future. So this is what our system looks like. We've got our transition matrix times the steady state vector equals the steady state vector. Now, in order to solve this system, we take this vector and we subtract it from the side, just like you do with regular algebra. Subtract it from the side, you move it over, and you get zeros on this side. This is what you're looking for. You've got this side moved over, and now there are zeros over here. Now we've got 3 equations and 3 unknowns. That's perfect. But because we're doing Markov chain methylation, we know the totality of the system, we actually have a 4th equation which helps us out. That is the amount, the percentage of DNA in the steady state that remains unmethylated or becomes hemimethylated or is fully methylated. Those percentages equal 1. This is the totality of the system. So 1U plus 1H plus 1F equals 100%. So put this all together in a system and you get this matrix. This is where it gets slightly complicated, so just bear with me. Notice that this upper part, these 3 equations, almost match this matrix up here. The only thing that's different is along the diagonal. Everything else is the same, and that is because when you do matrix multiplication, you get the top one times the top one, the middle one times the middle one, and the bottom one times the bottom one. And this will be minus this top one over here. It becomes one line. So since this is times the middle one and we're not subtracting any middle ones, the middle one remains the same. Since the bottom one, we're not subtracting any bottom ones, the bottom one remains the same. The only thing that changes is this first one, because if it's times a u and then minus a u, we get a negative number. If the probability of DNA remaining unmethylated was 20%, minus 1u over here, because there's 1 of them, you get a negative number. So these numbers along the diagonal will become negative, but the rest of the matrix remains the same. We've got our zeros over here. And then we've got our 4th equation, which is the 1 + 1 + 1 = 1. We've got that right there. These are all lined up with respect to the variables. And the way we solve the system is actually really simple. Use row reduction, Gauss-Jordan elimination. So the setup, this might be a little complicated. If it is, there's actually a really great video on YouTube. Just Google /YouTube steady state vectors for Markov chains, discrete mathematics, and they do some math for a two-state Markov chain. They make it really simple to follow. Here's the link if you want to click the link. I hope that all made sense. Thank you and goodbye.